Hello, my name is Michael Kurtz. This is my final project for physics. Um, so today we're going to be looking at a Rube Goldberg uh, machine, and what it is it's a physics machine of multiple different components that all come together to form a different task. Um, so we're going to start off here at 39 seconds. And what I want you to pay attention to is this red ball right here. Now, if we hit play, we can see the ball rolling down the hill. Now, the ball is accelerating down the ramp. Now, this acceleration is due to two of the forces that are acting on it. The force of gravity, which is acting straight down on the ball, and the normal force, which is not going to be directly opposite of gravity, so that's going to cause the ball to roll down the hill. Now, velocity, velocity is the speed of the ball at any one point in time. So if we were to stop the ball right here in that moment of time and take its speed, that is going to be our velocity. Now that's units is meters per second. So it's the amount of meters it has traveled from its original start point in 1 second. So that's how we talk about that in meters. Now, in terms of velocity and acceleration, there are positive and negative. But what we have to do as scientists is determine which direction is the negative direction. So we'll do anything to the right, anything moving to the right is positive, and anything moving to the left is negative. Now, we also have to determine positive and negative for moving up and down. Up is going to be positive for us, and down is going to be negative for us. Now, negative acceleration does not always mean slowing down. Negative acceleration, but moving in a negative direction actually means that the ball is speeding up. But negative acceleration in the positive velocity means that the ball is going to be slowing down. So we are going to so we can find the current velocity of this ball by adding the initial velocity to the multiplication of acceleration and the amount of time that has passed. Now that is one of our physics equations that we can use. So we're going to go ahead and hit play, and we're going to stop it at 1 minute and 2 seconds. Okay, so we're going to stop it right there. And now what I'm going to discuss is forces. I mentioned forces earlier with the force of gravity and the normal force acting upon an object. If we look here at the top of the screen, we can see a lock sitting on the table. Now, what's happening with that lock is gravity is acting on that lock, but the normal force of the table is pushing back with the exact same amount of force that gravity is pushing down on the lock. So the lock does not move. Now, once this ball, a little bit of a spoiler alert, this ball is going to bounce off this little spice container and knock the lock off the edge of the table. Now, once that lock gets knocked off the table, it's now in free fall. Now, when an object is in free fall, it will accelerate downward at the speed of 9.8 meters per second squared. Now, the force, how we determine the force of the lock is the force is created by the ball by multiplying the mass of the ball and the acceleration that the ball is going through. That's how we determine the force of the equation. I mean the force of the machine. So we're gonna watch ahead here. Sorry, the internet's been spotty today. So as you can see here, the cup is bouncing off rubber bands. Now that's an example of a spring force. Now spring forces we know this is a spring force because the rubber band is stretching and then returning to its original position. Now that uses the spring constant K to help determine the amount of force that the spring is putting off in one instance. Now, there are also things called frictional forces. Now, frictional forces are any surface has a certain amount of friction that an object has to overcome in order to move across that. And in order to cut down on the amount of issues they may have due to friction, they used a very smooth table here. Now, this table is going to allow the cup to just kind of slide rather than stick if it was a rougher surface or a stickier surface. So because this is smooth, the cup can now just slide down from rubber band to rubber band as we continue. Now, the way the ball in the previous, well, actually in the very beginning of this section when it was rolling down, the way that fights friction is because it's round, it actually rolls. So it rolls over what would cause the friction rather than just straight sliding across the surface. So we're going to skip a little ahead a little bit to 1 minute and 47 seconds. Okay, so we're going to be discussing work and energy right now. So work is the amount of force per meter that is going on in an object. What exactly is happening? How it is creating its motion and moving. So the direction of work depends on the direction we determine to be positive. So we're going to determine up to be positive, down to be negative, and anything lower than the table is negative. The work done by the gravitational forces on this apple here, which we will see in a second, we'll go ahead and watch that. So the lime is flying right now, and then the apple is going to roll, and so we just need that little split second where the apple was falling down. Now, the work done by the gravitational forces on the apple is as it drops into the basket is because it's thrown. We determined the work done by the gravitational force to be equal to the weight of the apple multiplied by the distance it is dropped. And its unit is Newton per meter. Now, I'm not going to talk about the blanketing effect of the little towel in here that kind of slowed it down because we really don't need to get into that. That's a lot more complicated physics than I really even know how to do. So next we're going to go to 2 minutes and 2 seconds. 2 minutes and 22 seconds, I apologize. And discuss momentum. So you want to be looking, oh my God, I'm so sick of technology. So if you look here at the mallet, this mallet is going to fall down and hit the spoon here. Now let's go ahead and watch that happen. Boom. Launches the ping pong ball. Now, what I want to talk about is the momentum of the hammer. So the hammer or the mallet is being knocked over by what looks to be a large domino brick here. And what's happening is as the mallet is falling and makes contact with that spoon, we're trying to determine how strong that is. So unlike force, which is force equals mass times acceleration, momentum focuses on multiplying the mass and the velocity. So we need to find the velocity by determining how fast the hammer was traveling when it made contact with the spoon. And we do this by by taking the distance of the hammer falling and multiplying it by the gravitational acceleration. So when we combine these two things, that's how we determine the velocity at a certain distance. So if the hammer's falling at a constant rate of 9.8 meters per second, we know that we can just multiply it by the distance it's traveling in order to determine its velocity at that current moment. We then multiply that velocity and the mass of the mallet to find the momentum of the hammer. So what we're doing now is now that we have found the velocity, we can plug it into, we can multiply it by the mass to determine the exact power of it at the exact moment that it contacted the spoon. I'm sorry. So we need the velocity to determine the momentum of the collision, which will then carry on through other forms of kinetic energy. So that energy could be dispersed in heat. It could be dispersed in the sound energy. It could be dispersed in a lot of different ways. There are a lot of forces that could act on an object in order to affect it in some way. So we're going to skip forward quite a bit to 3 minutes and 42 seconds here. 3 minutes and 42 seconds. So as you can see here, the salt rolls and then the turntable starts. So what I want to talk about is torque and rotational movement. So if we look here, we have a little bulldozer toy and we have the salt. Now, the bulldozer scoop is much closer to the center of the circle than the salt is. So if we watch it as it spins, the bulldozer will appear to be spinning a lot faster than the salt is currently spinning. Now let's go ahead and take a look at that. Yeah, you see how the salt appears to be traveling much slower but over more of a distance, while the bulldozer scoop is kind of spinning a lot quicker, even though they're really only traveling the exact same arc length. So the table turns at a constant angular velocity regardless of the radius. So both the salt here and the scoop of the bulldozer are going to have the same angular velocity regardless of how far they are from the center of the circle. Now, tangential velocity, on the other hand, increases with the radius. The radius times angular velocity is how we determine tangential velocity. So because we're further out from the center with the salt than we were the bulldozer, we have to multiply the radius by that angular velocity that we were discussing earlier, and we will find the tangential velocity for the bulldozer here. And we can also do the same thing by finding the radius of the salt and multiplying it by the angular velocity to determine its tangential velocity. Now, when we compare those together, they're not going to be the same. And that difference is going to be the difference that we appear to be seeing when it seems that the salt is not moving as fast as the bulldozer. So I think that is all for me today. I will get this posted. It's been a fun semester. I have really enjoyed learning physics, and I hope you have a good holidays. So thank you. Have a good one. Bye.